Imagine, for a moment, that you're looking up at the night sky, and you realize that among the countless stars, there's a good chance that some of them host planets with life. Not little green men or giant squids in the sky, but life. Maybe something like us, maybe something utterly alien. The question is, how do we find out? How do we know if we're not alone? That's where the search for biosignatures comes in. These are the subtle clues, the chemical fingerprints that life leaves behind, and they could be the key to one of the biggest discoveries in human history. So, let's dive in and explore how we're hunting for these signs of life in the atmospheres of distant worlds. The concept of biosignatures. Biosignatures are subtle indicators of life that can be detected in the atmospheres of planets. These signs are not direct evidence of life itself, but rather byproducts of biological processes. On Earth, for instance, oxygen is a prominent biosignature. It is abundant in our atmosphere due to photosynthesis, a process carried out by plants and certain microorganisms. Without life, Earth's atmosphere would likely have much less oxygen. Other potential biosignatures include methane, nitrous oxide, and even certain combinations of gases that are out of chemical equilibrium. These gases can hint at the presence of life, as their concentrations and ratios might be difficult to explain through non-biological processes alone. Detecting biosignatures in alien atmospheres is a complex task that relies on advanced technologies. Spectroscopy is one of the primary methods used to identify these signs of life. By analyzing the light that passes through a planet's atmosphere, scientists can determine the composition of gases present. Different molecules absorb light at specific wavelengths, leaving distinct fingerprints that can be detected by spectrometers. Space-based telescopes, such as the James Webb Space Telescope, are equipped with highly sensitive instruments capable of capturing these subtle signals. Additionally, future missions may employ specialized probes or orbiters to conduct in-situ analyses, providing even more detailed data about the atmospheres of exoplanets. The implications of finding biosignatures in alien atmospheres are profound. Discovering even the simplest forms of life beyond Earth would revolutionize our understanding of biology, chemistry, and the universe itself. It would suggest that life is not unique to Earth, potentially paving the way for a deeper exploration of extraterrestrial ecosystems. Moreover, identifying biosignatures could guide future missions to search for more complex life forms. However, it's crucial to approach this search with caution. False positives can occur, as some non-biological processes might mimic the signs of life. Therefore, scientists must carefully analyze and interpret the data to ensure the reliability of their findings. The search for biosignatures is not just about finding life. It's about understanding our place in the cosmos and the potential for life to exist elsewhere. Historical context of biosignature research. The quest to detect biosignatures in alien atmospheres has deep roots, intertwined with the evolution of astronomical and biological sciences. Initially, the concept of biosignatures was tied to the search for extraterrestrial life, a fascination that dates back to ancient times. However, it was not until the 20th century that scientists began to formalize the idea of using atmospheric composition as a marker for life. Early research focused on Earth's own biosphere, studying how life alters the atmosphere. For instance, oxygen, which makes up about 21% of Earth's atmosphere, is a clear biosignature, as it is produced predominantly by photosynthetic organisms. This understanding laid the groundwork for extending the search to other planets. Technological advancements played a pivotal role in shaping biosignature research. The development of spectroscopy, a technique that analyzes the interaction between matter and electromagnetic radiation, was a game-changer. Spectroscopy allows scientists to identify the chemical composition of a planet's atmosphere by examining the light that passes through it. Early spectroscopes were ground-based, but the launch of space telescopes like the Hubble Space Telescope revolutionized the field. These instruments provided unprecedented access to the atmospheres of exoplanets, those orbiting stars beyond our solar system. The detection of molecules like methane, another potential biosignature, in the atmospheres of exoplanets sparked excitement and speculation about the possibility of extraterrestrial life. The implications of finding biosignatures in alien atmospheres are profound. It would not only confirm that life exists beyond Earth, but also provide insights into the diversity and distribution of life in the universe. Scientists speculate that the detection of certain biosignatures could indicate the presence of microbial life, similar to that found on Earth. Others suggest that more complex biosignatures might hint at advanced, technologically capable civilizations. However, the interpretation of biosignatures is complex and requires careful consideration of false positives. For example, methane can be produced both biologically and abiotically, so its detection alone is not definitive proof of life. Despite these challenges, the search for biosignatures continues to be a driving force in astrobiology, pushing the boundaries of our understanding of life in the cosmos. The role of atmospheric science in astrobiology. Atmospheric science plays a pivotal role in astrobiology, particularly in the search for biosignatures, indicators of life, in the atmospheres of exoplanets. Biosignatures can be as straightforward as the presence of oxygen or methane, which on Earth are predominantly produced by living organisms. These gases, when detected in the right concentrations and contexts, could hint at the presence of life elsewhere in the universe. However, it's not just about finding these gases. It's about understanding their origins and the atmospheric conditions that might support life. This is where atmospheric science comes into play, providing the tools and knowledge to interpret these signals accurately. Current detection technologies, such as spectroscopy, allow scientists to analyze the light passing through an exoplanet's atmosphere. By examining the absorption lines in the spectrum, researchers can identify the chemical composition of the atmosphere. For instance, the James Webb Space Telescope, JWST, is equipped with instruments capable of detecting biosignatures in the atmospheres of exoplanets. These technologies are crucial for distinguishing between biological and abiotic sources of atmospheric gases. For example, methane can be produced both biologically and geologically, so its detection alone isn't a definitive sign of life. Contextual clues, such as the presence of other gases or specific atmospheric conditions, are necessary to make informed interpretations. The implications of finding biosignatures in alien atmospheres are profound. It would not only confirm that life exists beyond Earth, but also provide insights into the diversity and resilience of life in the universe. This knowledge could reshape our understanding of biology, chemistry, and even philosophy. Moreover, it could guide future missions to search for life, focusing on planets and moons with the most promising atmospheric conditions. The search for biosignatures is a multidisciplinary endeavor, combining astrophysics, chemistry, and biology. As our understanding of atmospheric science advances, so too will our ability to detect and interpret these potential signs of life, bringing us closer to answering one of humanity's most fundamental questions: are we alone in the universe? Key characteristics of biosignatures. Biosignatures are subtle indicators of life, often found in the atmospheres of planets. They are typically gases or combinations of gases that, due to their abundance or specific ratios, suggest the presence of biological processes. On Earth, for instance, oxygen makes up about 21% of the atmosphere, a level far too high to be maintained by abiotic processes alone. This is largely due to photosynthesis, a biological process. Similarly, methane, another potential biosignature, can be produced by microbial life and is often found in conjunction with oxygen, creating a detectable imbalance. Detecting these biosignatures in alien atmospheres is a complex task. Current technologies, such as those on board the James Webb Space Telescope, use spectroscopy to analyze the light passing through a planet's atmosphere. Different molecules absorb light at different wavelengths, leaving unique fingerprints that can be detected and identified. For example, oxygen absorbs light in the near-infrared range, while methane has distinct absorption features in the mid-infrared. By studying these spectral lines, scientists can infer the presence of specific molecules. However, these technologies are limited by the distance and size of the planets they observe. Smaller, Earth-sized planets orbiting distant stars present a significant challenge. The implications of finding biosignatures in alien atmospheres are profound. It would provide strong evidence for the existence of extraterrestrial life, even if it's only microbial. This could reshape our understanding of biology, evolution, and the universe itself. Moreover, it could guide future missions to study these planets more closely. For instance, if a planet shows signs of oxygen and methane, it might be a prime target for further investigation. However, it's crucial to remember that biosignatures are not definitive proof of life. They are indicators that warrant further study. Abiotic processes can sometimes mimic biological ones, so any detection would need to be carefully verified. Speculating on the implications, the discovery of biosignatures could also have philosophical and societal impacts. It would challenge our perception of life's uniqueness and perhaps even our place in the universe. It could inspire new fields of research, from astrobiology to planetary science, and drive technological advancements in telescope and spacecraft design. Furthermore, it could foster international collaboration, as the search for life beyond Earth is a unifying goal. However, it's also important to consider the potential for misinterpretation or miscommunication. False positives or sensationalized claims could lead to misunderstanding or even panic. Therefore, any detection would need to be handled with care, transparency, and rigorous scientific scrutiny. The habitable zone and its significance. The concept of the habitable zone, also known as the Goldilocks zone, is crucial in the search for biosignatures in alien atmospheres. This zone is the region around a star where the temperature is just right for liquid water to exist on the surface of an orbiting planet. Too close to the star, and the planet is too hot, causing water to evaporate. Too far away, and it's too cold, leading to frozen surfaces. Liquid water is a key ingredient for life as we know it, making the habitable zone a prime target in the search for extraterrestrial life. Planets within this zone receive the right amount of stellar radiation to maintain temperatures suitable for liquid water, setting the stage for potential habitability. Biosignatures are signs of life that can be detected in a planet's atmosphere. These can include gases like oxygen, methane, and carbon dioxide, which on Earth are often associated with biological processes. For instance, oxygen makes up about 21% of Earth's atmosphere and is primarily produced by photosynthesis, a process carried out by plants and certain microorganisms. Methane, another potential biosignature, can be produced by microbial life and is present in Earth's atmosphere in smaller quantities. Detecting these gases in the atmospheres of exoplanets could indicate the presence of life. However, it's important to note that these gases can also have abiotic sources, so their detection alone isn't definitive proof of life. Current and future technologies are being developed to detect these biosignatures. Spectroscopy is a key method, allowing scientists to analyze the light from a planet's atmosphere and identify the unique spectral signatures of different gases. Space telescopes like the James Webb Space Telescope, JWST, and the upcoming Habitable Worlds Observatory, HWO, are equipped with advanced spectrographs to study exoplanet atmospheres. Additionally, direct imaging techniques are being refined to block out the light from a star and capture the faint light reflected by an orbiting planet. This allows for a more detailed study of the planet's atmosphere and surface. The implications of finding biosignatures in alien atmospheres are profound. It could confirm that life exists beyond Earth, revolutionizing our understanding of biology and our place in the universe. It could also provide insights into the diversity of life and the conditions under which it can arise. However, it's essential to approach these findings with caution, as the interpretation of biosignatures can be complex and may require multiple lines of evidence. Planetary atmospheres, a brief overview. Planetary atmospheres are complex, dynamic systems that envelop worlds throughout the universe. They are composed of various gases, each with unique properties and behaviors. Earth's atmosphere, for instance, is a delicate balance of nitrogen, oxygen, argon, and trace amounts of other gases like carbon dioxide and methane. These components interact in intricate ways, driving weather patterns, climate, and the very conditions that support life. Other planets, such as Mars and Venus, have atmospheres vastly different from Earth's, with compositions that reflect their unique environments and histories. Atmospheres can reveal a great deal about a planet's potential to host life. Biosignatures, or indicators of biological activity, are often sought in these atmospheric compositions. For example, the presence of oxygen in significant quantities is a strong biosignature on Earth, as it is primarily produced by photosynthetic organisms. Similarly, methane can indicate biological processes, though it can also be produced abiotically. Scientists use sophisticated models and observations to interpret these atmospheric signatures, looking for patterns that might suggest the presence of life. Detection technologies have advanced significantly, enabling the study of exoplanetary atmospheres with unprecedented detail. Spectroscopy is a key tool in this endeavor, allowing scientists to analyze the light that passes through a planet's atmosphere. Different molecules absorb light at specific wavelengths, creating unique spectral fingerprints. By examining these fingerprints, researchers can identify the composition of an atmosphere and search for biosignatures. Space-based telescopes, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, are instrumental in these observations, providing high-resolution data from distant exoplanets. The implications of finding biosignatures in alien atmospheres are profound. It would not only confirm that life exists beyond Earth, but also provide insights into the diversity and resilience of life in the universe. This knowledge could reshape our understanding of biology, chemistry, and the potential for habitability on other worlds. Moreover, it would raise intriguing questions about the nature of life itself, its origins, and its potential to thrive in environments vastly different from Earth's. The search for biosignatures is not just a scientific pursuit. It is a journey to understand our place in the cosmos and the possibilities that lie beyond our home planet. Techniques for detecting biosignatures. The quest to find biosignatures in alien atmospheres is a captivating endeavor that combines astrobiology, planetary science, and cutting-edge technology. Biosignatures are indicators of life, such as certain gases or combinations of gases that suggest biological processes. On Earth, for instance, the presence of oxygen in our atmosphere is a strong biosignature, as it is largely produced by photosynthetic life. Detecting similar markers on exoplanets could hint at the presence of extraterrestrial life. Several techniques are employed to detect these elusive biosignatures. One of the most promising methods is spectroscopy, which involves analyzing the light that passes through a planet's atmosphere. Different molecules absorb light at specific wavelengths, leaving distinct fingerprints that can be detected by sophisticated instruments. For example, the James Webb Space Telescope, JWST, set to launch soon, will use its advanced spectrographs to study the atmospheres of exoplanets. By examining the spectra of light from these distant worlds, scientists hope to identify the unique signatures of molecules like oxygen, methane, and water vapor. Another technique involves direct imaging of exoplanets, which is incredibly challenging due to the overwhelming brightness of their host stars. Advanced coronagraphs and starshade technology are being developed to block out starlight, allowing astronomers to capture images of exoplanets directly. Once an image is obtained, spectrometers can analyze the light reflected or emitted by the planet to search for biosignatures. This method is particularly useful for studying planets that are relatively close to their stars, where atmospheric conditions might be more favorable for life. The implications of detecting biosignatures are profound. Finding evidence of life beyond Earth would revolutionize our understanding of biology, chemistry, and the universe itself. It could provide insights into the origins of life and the potential for life to exist elsewhere in the galaxy. Moreover, it would raise profound philosophical and ethical questions about our place in the cosmos and our responsibilities towards any extraterrestrial life forms we might encounter. The search for biosignatures is not just a scientific pursuit. It is a journey that could redefine humanity's perspective on life and our role in the universe. Spectroscopy, the primary tool. The quest to find biosignatures in alien atmospheres hinges significantly on the capabilities of spectroscopy. This scientific technique involves analyzing the interaction between matter and electromagnetic radiation, enabling scientists to determine the chemical composition of an atmosphere. Biosignatures, which are indicators of life, can be detected through specific patterns in the spectrum of light that passes through or is emitted by an atmosphere. For instance, the presence of oxygen, methane, or other gases in certain concentrations could suggest biological activity. Spectroscopy allows astronomers to dissect starlight that has interacted with an exoplanet's atmosphere, revealing these crucial clues. Modern spectroscopy employs a range of technologies, from ground-based telescopes to space-based observatories like the Hubble Space Telescope and the upcoming James Webb Space Telescope. These instruments use spectrographs to spread light into its component wavelengths, creating a spectrum that can be analyzed for absorption or emission lines characteristic of different molecules. For example, the detection of oxygen, O2, and methane, CH4, together could be a strong biosignature, as these gases are often produced by living organisms and would not typically coexist in large quantities without biological processes. Additionally, the presence of water vapor, H2O, is another key indicator, as it is essential for life as we know it. The implications of detecting biosignatures in alien atmospheres are profound. It would provide evidence of life beyond Earth, reshaping our understanding of biology, chemistry, and the universe itself. The discovery of even microbial life elsewhere would suggest that life might be more common than previously thought, potentially existing in numerous exoplanetary systems. This could also drive further technological advancements in spectroscopy and space exploration, as scientists strive to gather more detailed data from distant worlds. Moreover, it would raise intriguing questions about the nature of extraterrestrial life, its similarities and differences to life on Earth, and the potential for interstellar communication or even colonization. The search for biosignatures is not just a scientific endeavor, but a journey that could redefine humanity's place in the cosmos. Ground-based observations versus space-based observations. Ground-based observations have long been the backbone of astronomical research, offering a direct and cost-effective means to study the cosmos. Telescopes on Earth can detect biosignatures, which are chemical signs of life, by analyzing the light that passes through an exoplanet's atmosphere as it transits its host star. Spectroscopy is the primary technology used for this purpose. For instance, the Very Large Telescope, VLT, in Chile has been instrumental in detecting potential biosignatures like oxygen, methane, and water vapor. However, Earth's atmosphere can interfere with these observations, absorbing or emitting light at specific wavelengths, which can obscure the signals from exoplanetary atmospheres. Adaptive optic systems help mitigate this issue by correcting the distorting effects of Earth's atmosphere in real time. Space-based observations, on the other hand, provide a clearer and more uninterrupted view of the universe. Satellites like the Hubble Space Telescope and the upcoming James Webb Space Telescope, JWST, operate above Earth's atmosphere, avoiding the atmospheric interference that plagues ground-based observations. This allows for more precise and sensitive measurements of exoplanetary atmospheres. Space-based telescopes can also observe a wider range of wavelengths, including infrared and ultraviolet, which are often blocked by Earth's atmosphere. The JWST, for example, is equipped with advanced spectrographs designed to detect biosignatures with unprecedented sensitivity. Its instruments can analyze the chemical composition of exoplanetary atmospheres, looking for gases that might indicate the presence of life, such as oxygen, methane, and nitrous oxide. The implications of detecting biosignatures in alien atmospheres are profound. Finding evidence of life beyond Earth would revolutionize our understanding of biology, chemistry, and the universe itself. It could provide insights into the origins of life and the potential for life to exist elsewhere in the galaxy. Ground-based and space-based observations each have their strengths and limitations. Ground-based telescopes are more accessible and can be upgraded more easily, while space-based telescopes offer unparalleled clarity and a broader range of observational capabilities. Future advancements in technology, such as larger ground-based telescopes with advanced adaptive optics and next-generation space telescopes, will further enhance our ability to search for biosignatures. The synergy between these two approaches will be crucial in the ongoing quest to answer one of humanity's most fundamental questions: are we alone in the universe? The James Webb Space Telescope's contribution. The quest to find biosignatures in alien atmospheres has taken a significant leap forward with the advent of the James Webb Space Telescope, JWST. Biosignatures are chemical substances or processes that indicate the presence of life. They can be as straightforward as the oxygen we breathe or as complex as the chlorophyll that gives plants their green hue. These markers are what scientists look for when scanning the atmospheres of exoplanets, those planets that orbit stars beyond our solar system. The JWST, with its advanced infrared capabilities, is uniquely equipped to detect these subtle signs of life. One of the primary technologies employed by the JWST is spectroscopy. This method involves analyzing the light that passes through a planet's atmosphere. Different molecules absorb light at specific wavelengths, leaving distinct fingerprints that can be detected by the telescope. For instance, oxygen absorbs light at a wavelength of about 0.76 micrometers, while methane absorbs at around 3.3 micrometers. By examining these absorption lines, scientists can infer the presence of various molecules. The JWST's near-infrared spectrograph, NIR-SPEC, and mid-infrared instrument, MIRI, are particularly adept at this task, allowing for the detection of a wide range of potential biosignatures. The implications of finding biosignatures in alien atmospheres are profound. It would not only confirm that life exists beyond Earth, but also provide insights into the diversity and distribution of life in the universe. For example, the detection of oxygen and methane together could indicate the presence of photosynthetic life, similar to what we have on Earth. Conversely, the presence of other molecules, like phosphine, could hint at entirely different forms of life. The JWST's ability to study the atmospheres of exoplanets in such detail opens up new avenues for astrobiology, the study of life in the universe. It brings us closer to answering one of humanity's most enduring questions: are we alone in the cosmos? Moreover, the JWST's contributions extend beyond mere detection. By studying the atmospheres of exoplanets, scientists can also learn about the environmental conditions on these distant worlds. For instance, the presence of certain biosignatures might indicate a planet's ability to support liquid water, a crucial ingredient for life as we know it. The telescope's data can also help scientists understand the atmospheric composition and dynamics of exoplanets, providing a broader context for the potential habitability of these worlds. This holistic approach not only enhances our understanding of biosignatures, but also deepens our appreciation for the complexity and diversity of planetary systems. Future space missions and their objectives. The search for biosignatures in alien atmospheres is a burgeoning field, with future space missions poised to revolutionize our understanding of life beyond Earth. Biosignatures are measurable indicators of life, such as specific gases in an atmosphere or unusual light patterns that suggest biological processes. These signs could hint at the presence of life, even if it's vastly different from what we know on Earth. For instance, the presence of oxygen and methane together in an atmosphere could be a strong biosignature, as these gases can indicate biological activity. Other potential biosignatures include nitrous oxide, sulfur compounds, and even certain patterns in light that might suggest photosynthesis or other biological processes. Upcoming missions are set to employ advanced technologies to detect these biosignatures. The James Webb Space Telescope, JWST, for example, is equipped with instruments that can analyze the atmospheres of exoplanets, looking for the spectral signatures of various gases. By observing how starlight filters through an exoplanet's atmosphere, scientists can identify the presence of specific molecules. Similarly, the upcoming European Space Agency's Aerial, Atmospheric Remote Sensing Infrared Exoplanet Large Survey mission aims to study the atmospheres of hundreds of exoplanets, focusing on their chemical composition and potential biosignatures. These missions will provide a wealth of data, helping scientists refine their understanding of what constitutes a reliable biosignature. The implications of finding biosignatures in alien atmospheres are profound. It would confirm that life exists beyond Earth, reshaping our understanding of biology, chemistry, and perhaps even philosophy. It could also guide future missions to search for life directly, such as landing on exoplanets or their moons to look for physical evidence. Moreover, the discovery of extraterrestrial life, even in microbial form, would have significant cultural and societal impacts, challenging our perceptions of our place in the universe. However, it's crucial to approach these findings with caution, as non-biological processes can sometimes mimic biosignatures. For example, volcanic activity or photochemical reactions can produce gases that might be mistaken for signs of life. Therefore, scientists will need to carefully analyze and interpret the data, considering all possible explanations. In the coming decades, space missions will continue to push the boundaries of our knowledge, bringing us closer to answering one of humanity's most fundamental questions. Are we alone in the universe? The search for biosignatures is a critical step in this journey, offering a tantalizing glimpse into the potential diversity of life in the cosmos. As our detection technologies advance, so too will our ability to interpret the data, paving the way for exciting discoveries and a deeper understanding of life's potential in the universe. The Goldilocks zone, balancing planetary conditions. The Goldilocks zone, also known as the habitable zone, is the orbital region around a star where the conditions might be just right for liquid water to exist on a planet's surface. This zone is not a fixed distance, but varies depending on the star's size and temperature. For instance, smaller, cooler stars have their habitable zones closer in, while larger, hotter stars have them further out. Within this zone, planets can receive the right amount of stellar radiation to maintain temperatures suitable for liquid water, a crucial ingredient for life as we know it. Biosignatures are measurable signs of life, and they can be either direct or indirect. Direct biosignatures include actual life forms or their components, like microbial fossils. Indirect biosignatures, which are more relevant for atmospheric studies, are chemical compounds or patterns that suggest the presence of life. For example, on Earth, oxygen and methane are prominent biosignatures. Oxygen is produced in large quantities by photosynthesis, and methane is often associated with biological processes. Detecting these gases in an exoplanet's atmosphere could hint at the presence of life. However, it's essential to consider that non-biological processes can also produce these gases, so their detection should be met with cautious optimism. To detect these biosignatures, scientists use a variety of technologies. Spectroscopy is a key method, allowing researchers to analyze the light from a planet's atmosphere and identify the unique spectral fingerprints of different gases. Space-based telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope are equipped with advanced spectrographs for this purpose. Additionally, future missions like the European Space Agency's Aerial, Atmospheric Remote Sensing Infrared Exoplanet Large Survey are designed to focus specifically on characterizing exoplanet atmospheres. These technologies are pushing the boundaries of our ability to search for life beyond Earth. The implications of finding biosignatures in alien atmospheres are profound. It would revolutionize our understanding of life in the universe, suggesting that life might be more common than previously thought. It could also provide insights into the origins of life and the conditions that make it possible. However, it's crucial to approach this search with caution. False positives are a real risk, and the detection of a potential biosignature would need to be confirmed through multiple lines of evidence. Moreover, the discovery of extraterrestrial life, even if only microbial, would have significant philosophical, ethical, and societal implications. It would force us to reconsider our place in the universe and our relationship with other forms of life. Atmospheric composition and biosignature detection. The quest to find biosignatures in alien atmospheres is a thrilling frontier in astrobiology. Biosignatures are indicators of life, and they can be as subtle as a particular mix of gases or as complex as patterns in light reflected by an organism. On Earth, life has left its mark on the atmosphere, with oxygen and methane being two key biosignatures. These gases are out of chemical equilibrium, meaning they shouldn't exist in such high concentrations together without a constant source, like life, to replenish them. Scientists are now looking for similar imbalances in the atmospheres of exoplanets, hoping to find clues that life might exist beyond Earth. Detecting these biosignatures is no easy task. Current technologies, like the James Webb Space Telescope, JWST, use spectroscopy to analyze the light passing through an exoplanet's atmosphere. Different molecules absorb light at different wavelengths, leaving unique fingerprints that can be detected. For instance, oxygen absorbs light in the near-infrared, while methane has distinct absorption features in the mid-infrared. By studying these spectra, scientists can infer the composition of an exoplanet's atmosphere. However, These signals are often weak and can be obscured by clouds or the host star's light, making detection challenging. The implications of finding biosignatures are profound. It would revolutionize our understanding of life in the universe, showing that life can emerge and persist in conditions different from those on Earth. It could also guide future missions to study these planets more closely, perhaps even searching for direct signs of life. However, it's crucial to remember that biosignatures aren't definitive proof of life. They're more like clues that need to be investigated further. For example, oxygen can also be produced abiotically through processes like the photolysis of water vapor. Therefore, any potential biosignature detection would need to be studied in context, considering the planet's environment and history. Moreover, the search for biosignatures isn't limited to gases. Light reflected by a planet's surface or atmosphere can also reveal signs of life. For instance, vegetation on Earth reflects light in a unique way, creating a red edge in the spectrum. This is due to the way chlorophyll absorbs visible light for photosynthesis but reflects infrared light. If we found a similar feature on an exoplanet, it could indicate the presence of plant-like life. However, this too has its challenges. The signal is often weak and can be mimicked by non-biological processes. Therefore, scientists would need to consider multiple lines of evidence before concluding that life exists on another planet. Common biosignature gases, oxygen, methane, and more. In the quest to find life beyond Earth, scientists are focusing on detecting biosignature gases in the atmospheres of exoplanets. These gases are byproducts of life processes and can indicate the presence of biological activity. Oxygen, methane, and other gases are at the forefront of this search, each with unique properties and implications. Oxygen, for instance, is a strong biosignature gas. On Earth, it is primarily produced by photosynthesis, a process carried out by plants, algae, and cyanobacteria. Detecting oxygen in an exoplanet's atmosphere could suggest the presence of photosynthetic life. However, oxygen can also be produced abiotically through processes like the photolysis of water molecules. Therefore, its detection alone isn't definitive proof of life, but it's a compelling clue. Scientists often look for oxygen in conjunction with other biosignature gases to strengthen their case. Methane is another intriguing biosignature gas. On Earth, it's produced by both biological and geological processes. Microorganisms in wetlands, for example, release methane as a byproduct of their metabolism. But methane can also be emitted by volcanoes and hydrothermal vents. The key to distinguishing between biological and geological sources lies in the ratio of methane to other gases and the rate of its production. A high concentration of methane, especially when accompanied by other biosignature gases, could hint at biological activity. Detection technologies for these gases are advancing rapidly. Spectroscopy is the primary method used to identify atmospheric compositions. By analyzing the light that passes through a planet's atmosphere, scientists can determine which gases are present. Space-based telescopes like the James Webb Space Telescope, JWST, and future missions like the Habitable Exoplanet Observatory, HabEx, are equipped with advanced spectrographs to study exoplanet atmospheres in detail. Additionally, ground-based observatories are also contributing to this effort, using high-resolution spectrographs to analyze the atmospheres of nearby exoplanets. The implications of detecting biosignature gases are profound. It could provide evidence of life beyond Earth, revolutionizing our understanding of biology and the universe. However, it's crucial to approach this search with caution. False positives are a significant concern, as some gases can be produced both biologically and abiotically. Therefore, scientists are developing sophisticated models and techniques to distinguish between these sources. The search for biosignature gases is a complex, interdisciplinary endeavor, but one that holds immense promise for our quest to understand life in the universe. False positives, challenges in interpretation. The search for biosignatures in alien atmospheres is a thrilling frontier in astrobiology. Biosignatures are measurable indicators of life, such as specific gases or combinations of gases that suggest biological processes. For instance, on Earth, the presence of oxygen, O2, and methane, CH4, In our atmosphere is a strong biosignature, as these gases are primarily produced by living organisms. Detecting such signatures on exoplanets could hint at the presence of extraterrestrial life. However, interpreting these signals is fraught with challenges, particularly the risk of false positives. False positives occur when non-biological processes mimic the biosignatures we associate with life. For example, oxygen can be produced abiotically through processes like water photolysis driven by stellar radiation. Similarly, methane can be generated by volcanic activity or chemical reactions in the atmosphere. To complicate matters, the context in which these gases are found is crucial. On Earth, oxygen and methane coexist because life continuously replenishes them, creating a disequilibrium that is a strong biosignature. However, on an exoplanet, finding these gases together might not necessarily indicate life if the planetary conditions allow for their simultaneous abiotic production. Detection technologies play a pivotal role in identifying potential biosignatures. Spectroscopy is the primary tool used to analyze the chemical composition of exoplanetary atmospheres. By examining the light that passes through an exoplanet's atmosphere during a transit, scientists can identify the unique spectral fingerprints of different molecules. Advanced telescopes like the James Webb Space Telescope, JWST, and upcoming missions such as the Habitable Worlds Observatory, HWO, are designed to enhance our ability to detect and interpret these signals. However, even with cutting-edge technology, distinguishing between biological and abiotic sources remains a significant challenge. The implications of false positives are profound. Misinterpreting a non-biological signal as a biosignature could lead to premature conclusions about the existence of extraterrestrial life, potentially diverting resources and attention away from more promising candidates. Conversely, dismissing a genuine biosignature as a false positive could delay the recognition of actual life. To mitigate these risks, scientists employ a multifaceted approach, combining atmospheric modeling, laboratory experiments, and comparative planetology. By studying a diverse range of planetary environments, including those within our own solar system, researchers can better understand the context in which false positives might arise and refine their interpretive frameworks. This nuanced approach is essential for navigating the complexities of the search for life beyond Earth. The role of context in biosignature detection. Biosignatures, the subtle indicators of life, are not just about finding a single molecule or signal. They are about understanding the context in which these signs appear. For instance, methane in an atmosphere could be a biosignature, but it could also be produced by volcanic activity or other geological processes. This is where context becomes crucial. Scientists need to consider the planetary environment, the chemical composition of the atmosphere, and the presence of other potential biosignatures to make a more informed interpretation. Detection technologies play a pivotal role in this context-driven approach. Spectroscopy, for example, is a powerful tool that analyzes the light absorbed or emitted by a planet's atmosphere. Different molecules absorb light at different wavelengths, creating a unique spectral fingerprint. By studying these fingerprints, scientists can identify the presence of specific molecules. However, the interpretation of these spectral data requires context. A spike in oxygen might be a sign of life, but it could also be a result of abiotic processes. This is why scientists look for multiple biosignatures and consider the planetary context. The implications of this context-driven approach are profound. It means that the search for life is not just about finding a single, definitive sign. Instead, it's about piecing together a complex puzzle. Each biosignature is a piece of this puzzle, and the context in which it appears provides the framework. For example, the presence of methane and oxygen together might be a stronger indication of life than either molecule alone. This approach also means that our understanding of life and the conditions it can thrive in is constantly evolving. As we learn more about the diversity of life on Earth and the extreme environments it can inhabit, we broaden our perspective on what to look for in the search for extraterrestrial life. Moreover, the role of context extends beyond the immediate planetary environment. It also encompasses our understanding of the universe as a whole. For instance, the location of a planet within its star's habitable zone, the type of star it orbits, and the galactic environment all provide crucial context. A planet might have the right atmospheric composition, but if it's constantly bombarded by high-energy radiation, the likelihood of life existing there diminishes. Therefore, the search for biosignatures is not just a scientific endeavor, but a holistic exploration that requires interdisciplinary knowledge and a nuanced understanding of the cosmos. Comparative planetology, learning from Earth and beyond. The search for biosignatures in alien atmospheres has become a focal point in modern astrobiology. Biosignatures are measurable indicators of life, such as specific gases or combinations of gases that suggest biological processes. On Earth, oxygen and methane are prominent biosignatures, produced predominantly by photosynthesis and microbial activity, respectively. Scientists are now looking for similar markers on exoplanets, using Earth as a reference point. Comparative planetology, the study of planets within and beyond our solar system, provides a framework for understanding the conditions that might harbor life. By comparing Earth's atmosphere with those of other planets, researchers can identify potential biosignatures and refine their search strategies. Detection technologies have advanced significantly, enabling the study of exoplanetary atmospheres in unprecedented detail. Spectroscopy is a key tool in this endeavor, allowing scientists to analyze the light passing through a planet's atmosphere and identify the unique spectral fingerprints of different molecules. Space-based telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope, JWST, are equipped with advanced spectrographs that can detect trace gases in exoplanetary atmospheres. Ground-based observatories, such as the Very Large Telescope, VLT, in Chile, also contribute to these efforts. These instruments are sensitive enough to discern subtle variations in atmospheric composition, which could indicate the presence of biosignatures. The implications of finding biosignatures in alien atmospheres are profound. Discovering life beyond Earth would revolutionize our understanding of biology, chemistry, and the universe itself. It could provide insights into the origins of life and the potential for life to exist in diverse environments. Moreover, it would raise philosophical and ethical questions about our place in the cosmos and our responsibilities towards any extraterrestrial life forms. The search for biosignatures is not just a scientific endeavor. It is a quest to answer one of humanity's most fundamental questions. Are we alone in the universe? Exoplanets versus solar system bodies. The search for biosignatures, or signs of life, in alien atmospheres has become a thrilling frontier in astrobiology. Scientists are keenly focused on two primary arenas: exoplanets and solar system bodies. Each offers unique challenges and opportunities for detecting potential signs of life. Exoplanets, planets orbiting stars outside our solar system, present a vast canvas for exploration. Their diversity in size, composition, and distance from their host stars provides a wide range of conditions that could harbor life. Solar system bodies, on the other hand, are more accessible for direct study, offering a closer look at environments that might support life. Biosignatures can take many forms, but atmospheric gases often steal the spotlight. On Earth, oxygen and methane are prominent biosignatures, produced predominantly by living organisms. Detecting similar gases in the atmospheres of exoplanets or on bodies like Mars or Europa could hint at biological activity. However, it's crucial to consider context. For instance, methane can also be produced abiotically through geological processes. Therefore, scientists look for combinations of gases and other indicators that together suggest life. Spectroscopy is the go-to technology for detecting these biosignatures. By analyzing the light that passes through a planet's atmosphere, scientists can identify the unique spectral fingerprints of different gases. Advanced telescopes like the James Webb Space Telescope, JWST, are pushing the boundaries of this technology, enabling the study of exoplanet atmospheres with unprecedented detail. In our solar system, missions to Mars, Europa, and Enceladus are equipped with sophisticated instruments to search for biosignatures. The Curiosity and Perseverance rovers on Mars are analyzing the planet's soil and atmosphere for signs of past or present life. Europa Clipper, a mission set to launch in the near future, will investigate Jupiter's moon Europa, which harbors a subsurface ocean beneath its icy crust. Similarly, the Cassini mission provided valuable data on Saturn's moon Enceladus, revealing plumes of water vapor and ice that could contain organic molecules. These missions combined direct sampling, imaging, and spectroscopic analysis to build a comprehensive picture of potential habitability. The implications of finding biosignatures, whether on exoplanets or solar system bodies, are profound. It would revolutionize our understanding of life in the universe, answering fundamental questions about our place in the cosmos. Moreover, it could guide future exploration and the search for extraterrestrial intelligence. However, false positives and negatives are significant challenges. The detection of a single biosignature might not be conclusive, necessitating further investigation. For example, the presence of oxygen alone doesn't guarantee life, as it can be produced through non-biological processes like photolysis of water molecules. Therefore, scientists must rely on a multifaceted approach, combining atmospheric data with geological and environmental context. The search for biosignatures is a complex, interdisciplinary endeavor that continues to captivate the scientific community and the public alike. The potential for technosignatures. The quest for biosignatures in alien atmospheres has long captivated scientists and enthusiasts alike. Biosignatures are measurable indicators of life, such as the presence of oxygen, methane, or other gases that, on Earth, are strongly associated with biological processes. These signatures can be detected through spectroscopy, a technique that analyzes the light spectrum of a planet's atmosphere to identify the unique fingerprints of different molecules. For instance, the James Webb Space Telescope, JWST, with its advanced infrared capabilities, can scrutinize the atmospheres of exoplanets, potentially revealing the telltale signs of life. Similarly, ground-based observatories like the Very Large Telescope, VLT, in Chile employ high-resolution spectrographs to dissect the chemical compositions of distant worlds. The implications of discovering biosignatures are profound, suggesting that life might not be unique to Earth and could be more common than previously thought. While biosignatures focus on detecting life as we know it, technosignatures take the search a step further by looking for evidence of advanced civilizations. Technosignatures could include artificial atmospheric pollutants, industrial chemicals, or even structures like Dyson spheres that harness the energy of stars. One of the most promising technosignatures is the detection of technogenic gases, such as chlorofluorocarbons, CFCs, which are synthetic compounds with no natural counterparts on Earth. These gases, if found in an exoplanet's atmosphere, could indicate the presence of industrial activity. Another intriguing possibility is the detection of radio signals or laser emissions, which could be deliberate attempts at communication or unintended leakage from advanced technologies. The search for technosignatures is still in its infancy, but projects like the Breakthrough Listen initiative are actively scanning the skies for any signs of intelligent life. The detection of technosignatures would have monumental implications for our understanding of the universe and our place within it. It would confirm that we are not alone, potentially leading to a paradigm shift in science, philosophy, and culture. The discovery could also provide insights into the longevity and sustainability of advanced civilizations, offering valuable lessons for our own future. However, the search for technosignatures is fraught with challenges. The vast distances involved mean that any signals would be incredibly faint, requiring highly sensitive instruments and sophisticated data analysis techniques. Additionally, the diversity of potential technosignatures makes it difficult to know exactly what to look for. Despite these hurdles, the potential payoff is immense, driving scientists to push the boundaries of technology and exploration. Ethical considerations in the search for life. The search for biosignatures in alien atmospheres is a thrilling frontier in astrobiology, driven by the quest to find evidence of life beyond Earth. Biosignatures are measurable indicators of life, such as specific gases in an atmosphere that are produced by biological processes. For instance, on Earth, oxygen and methane are prominent biosignatures, as they are primarily generated by photosynthesis and microbial activity, respectively. Detecting similar patterns in the atmospheres of exoplanets could hint at the presence of extraterrestrial life. However, identifying these biosignatures is a complex task, requiring sophisticated technologies and careful interpretation of data. Current and future telescopes, such as the James Webb Space Telescope, JWST, and upcoming missions like the Habitable Exoplanet Observatory, HabEx, are equipped with advanced spectrographs that can analyze the chemical composition of exoplanet atmospheres. These instruments work by capturing starlight that has passed through an exoplanet's atmosphere during a transit. Different molecules absorb light at specific wavelengths, leaving distinct fingerprints that can be detected and analyzed. For example, the presence of oxygen could be detected by observing absorption lines in the infrared spectrum. However, these technologies are not foolproof. False positives can occur, as some non-biological processes can also produce biosignature gases. For instance, methane can be generated by volcanic activity or chemical reactions in the atmosphere. The implications of discovering biosignatures are profound. Confirming the existence of life beyond Earth would fundamentally alter our understanding of biology, chemistry, and the universe itself. It could provide insights into the origins of life and the potential for life to exist elsewhere in the cosmos. However, the search for biosignatures also raises ethical considerations. One major concern is the potential for misinterpretation or miscommunication of findings. False positives or premature announcements could lead to unwarranted excitement or panic. It's crucial to approach the search for biosignatures with caution, ensuring that any potential discoveries are thoroughly vetted and communicated responsibly. Additionally, the discovery of extraterrestrial life could have significant cultural, philosophical, and religious implications. Societies around the world may react differently to such a revelation, and it's important to consider these potential impacts. The impact of discovering extraterrestrial life. The search for biosignatures in alien atmospheres is a thrilling frontier in astrobiology. Biosignatures are measurable indicators of life, such as specific gases or combinations of gases that are produced by biological processes. On Earth, for instance, oxygen and methane are prominent biosignatures. Oxygen makes up about 21% of our atmosphere and is largely a result of photosynthesis by plants and microorganisms. Methane, while present in smaller quantities, is produced by biological processes like digestion in animals and decomposition of organic matter. Detecting similar patterns in the atmospheres of exoplanets could hint at the presence of extraterrestrial life. Current technologies for detecting biosignatures rely heavily on spectroscopy, the study of the interaction between matter and electromagnetic radiation. Telescopes equipped with spectrographs can analyze the light from distant stars as it passes through an exoplanet's atmosphere. Different molecules absorb light at specific wavelengths, creating unique spectral fingerprints. For example, the James Webb Space Telescope, JWST, launched recently, is designed to observe the infrared spectrum, where many biosignature gases like methane and water vapor have strong absorption features. By dissecting this light, scientists can identify the chemical composition of an exoplanet's atmosphere and potentially detect biosignatures. The implications of discovering extraterrestrial life, even in microbial form, would be profound. It would fundamentally alter our understanding of biology, chemistry, and the universe itself. For one, it would provide evidence that life is not unique to Earth, suggesting that the universe is teeming with life in various forms. This could spur a new era of scientific exploration and technological innovation. Additionally, it would raise profound philosophical and existential questions. How would different cultures and religions interpret this discovery? Would it unite or divide humanity? The answers to these questions are as vast and complex as the universe we inhabit. Moreover, the discovery could also influence our environmental policies and practices. Knowing that life exists elsewhere might instill a greater sense of responsibility towards protecting and preserving our own planet. Interdisciplinary collaboration in astrobiology. Astrobiology, the study of life's origins, evolution, distribution, and future in the universe, thrives on interdisciplinary collaboration. This field brings together experts from astronomy, biology, chemistry, geology, and planetary science to tackle complex questions about life beyond Earth. Biosignatures, the measurable signs of life, are a hot topic in this interdisciplinary dance. They can be as straightforward as the presence of oxygen in an exoplanet's atmosphere, or as intricate as the detection of specific molecules that hint at metabolic processes. The search for these biosignatures is not a solitary endeavor. It's a symphony of diverse scientific disciplines working in harmony. Detection technologies are at the heart of this collaborative effort. Astronomers develop advanced telescopes and instruments to peer into the atmospheres of distant exoplanets. Spectroscopy, for instance, allows scientists to analyze the light passing through an exoplanet's atmosphere, revealing the chemical composition. Biologists contribute by identifying the molecular signatures of life as we know it, while chemists help understand the reactions and interactions that could produce these signatures. Geologists provide insights into the planetary conditions that might support or hinder life. Each discipline brings its unique perspective and tools to the table, enriching the search for biosignatures. The implications of finding biosignatures are profound. It could revolutionize our understanding of life's place in the universe. If life is discovered elsewhere, it would suggest that the emergence of life might be a common occurrence, given the right conditions. This could reshape our philosophical, theological, and scientific worldviews. Moreover, it could drive technological advancements in detection methods and space exploration. However, the absence of biosignatures in the near future doesn't necessarily mean we're alone. It might simply indicate that our current technologies are not yet sophisticated enough to detect the subtle signs of extraterrestrial life. The search is ongoing, and each step forward brings us closer to answering one of humanity's most profound questions: are we alone in the universe? Public engagement and science communication. The search for biosignatures in alien atmospheres has captivated public imagination and sparked a wave of scientific communication efforts. Biosignatures are measurable indicators of life, such as specific gases in an atmosphere that living organisms produce or consume. For instance, oxygen, methane, and nitrous oxide are all potential biosignatures on Earth. Scientists are now looking for these or similar gases in the atmospheres of exoplanets, planets orbiting other stars, to infer the presence of life. The James Webb Space Telescope, JWST, launched in 2021, is one of the key tools in this endeavor. It can analyze the light filtering through an exoplanet's atmosphere during a transit, revealing the chemical composition of that atmosphere. This method, known as transit spectroscopy, is revolutionizing the field of astrobiology. Public engagement in this area is crucial, as it bridges the gap between complex scientific research and general understanding. Museums, documentaries, and online platforms play a significant role in making this science accessible. For example, NASA's Exoplanet Exploration Program offers interactive tools and visualizations that allow the public to explore exoplanets and their potential habitability. Social media campaigns, such as those by the European Space Agency, ESA, also demystify the search for biosignatures, making it relatable and exciting. The involvement of citizen scientists who participate in projects like Zooniverse Planet Hunters further democratizes the search for life beyond Earth. These initiatives not only educate, but also inspire the next generation of scientists and space enthusiasts. The implications of finding biosignatures are profound. Discovery of life, even in microbial form, would fundamentally alter our understanding of life's prevalence in the universe. It would raise philosophical, ethical, and scientific questions about our place in the cosmos. For instance, the detection of oxygen on an exoplanet might suggest photosynthesis, a process central to life on Earth. However, scientists must also consider false positives. Some non-biological processes, like volcanic activity or photochemical reactions, can produce similar gases. Thus, the search for biosignatures is not just about finding a single gas, but understanding the context and co-occurrence of multiple indicators. This nuanced approach ensures that any potential discovery is robust and scientifically sound. Effective science communication in this field requires balancing excitement with caution. While the prospect of finding alien life is thrilling, it's essential to convey the rigorous process behind such discoveries. Public engagement efforts should highlight the iterative nature of science, where hypotheses are tested and refined over time. For example, the discovery of phosphine in Venus's atmosphere in 2020 sparked intense debate and further research, illustrating how scientific inquiry progresses. By emphasizing this process, communicators can foster a deeper appreciation for the scientific method and the quest to understand our place in the universe. Ultimately, the search for biosignatures is not just a scientific endeavor, but a shared human journey. As we wrap up our journey into the search for biosignatures in alien atmospheres, let's recap the key points that have guided our exploration. Biosignatures are essentially the fingerprints of life, unique chemical signatures that hint at the presence of living organisms. These can include gases like oxygen, methane, or even more complex molecules that suggest biological processes. Detecting these signs involves advanced technologies, such as spectrographs that analyze the light passing through an exoplanet's atmosphere, revealing the chemical composition hidden within. The implications of finding biosignatures are profound. It would not only answer the age-old question of whether we are alone in the universe, but also reshape our understanding of life itself. Imagine the possibilities. Discovering life forms that thrive in conditions vastly different from those on Earth, or finding that life is more common than we ever imagined. Each discovery would be a step closer to unraveling the mysteries of the cosmos and our place within it. As we look to the future, the search for biosignatures is just beginning. New telescopes, like the James Webb Space Telescope, are already pushing the boundaries of what we can observe, and upcoming missions promise to delve even deeper into the atmospheres of distant worlds. The next breakthrough could be just around the corner, and you could be part of this incredible journey. So what's next? Stay tuned for our upcoming series on the latest advancements in exoplanet research. We'll explore the cutting-edge technologies and the brilliant minds behind them, bringing you closer to the frontiers of space exploration. Don't forget to like, share, and subscribe to join us on this thrilling adventure. Together, let's gaze into the stars and uncover the secrets of the universe.